K relates to the energy. K is equal square root of 2me over h bar squared. So we can use this K, this value of energy here instead of K. Let's see, what do we get? If we substitute, then we get values for E, which depends on N. Okay, so actually what we get is 2 2m E over h bar squared, which is k squared, should be equal to n squared pi squared over L squared. Because what I have here on the left-hand side is my k squared, right? Okay, where n is equal to this. So I can find E. So E is actually given by this. You see, the energy of the electron inside this region is actually, the electron can have different energies. These energies depend on the number n. And this number is an integer, 1, 2, 3, etc. Now, since I have n squared, it doesn't matter if it's positive or negative. So I'm going only to take the positive values. But the very important thing is the electron can have separate energies depending on n equals 1, 2, 3. So what we're talking about here is that energies are quantized from quantum mechanics. Quantized meaning the energy, here we have the box or the region of length L. The energy, here is the energy of the electron, say. The energy of the electron can be this value here, or this value here, or this value here, or this value here. This is E1 for n equals 1. So if we substitute n equals 1 here, we get pi squared h bar squared over 2ml squared. That is my E1, okay, which is this energy. And then the second energy, that is allowed. You see, I'm using the word allowed energy. And that allowed energy is a very important word because only these energies are allowed, okay? And so here is E2 for n equals 2. So the electron can have this energy, which is, if you substitute n equals 2, you get E2 actually equals 4 E1, right? And then here is E3, which is for n equals 3. And again, if you substitute for n equals 3, you find A3 equals 9 E1. So what we're saying is that the energy of the electron inside this region cannot be in between here, or in between here, or in between here. It can only be at this value, or this value, or this value, or this value. These are the allowed energies. This is energy quantization. These regions here of energies are not allowed. So these regions of energies are forbidden energy gaps. We cannot have the energy of the electron here. Now, this is entirely different from classical mechanics. Classical mechanics tells us that the energy of the electron can be any energy, right? As long as it is in a zero potential, if we give it thermal energy or optical energy, if we heat it, if we do anything, doesn't matter if it's confined, we will always have some energy. It can have any energy. Quantum mechanics says no. If there is confinement and the electron cannot leave a certain region, then you cannot have all energies. You only have a set of energies, which are called allowed energies. And in between these allowed energies, you have forbidden energies that the electrons can never have. Okay? So that's a very important conclusion, important finding. And as I told you at the beginning, that we believe quantum mechanics when it comes to these very small particles. So our energy of the particle is quantized and it has discrete. You see now the term I'm using, discrete energy states. Discrete meaning separated from one another. They are not continuous. In classical mechanics, they are continuous. Okay? Now, since we know from here, right, if we clean this again a little bit, and clean this a little bit here, then we know K, and if we substitute K here, and we know from that boundary condition phi is 0, then the solution, the wave function, is a sine n pi x L, again for different n equals 1, 2, 3, etc. And for each one of these states, energy states, or wave functions, these are called energy states or eigenstates. Okay, eigenstates. These n, 1, 2, 3, etc., these are called eigen numbers or quantum numbers, right? So n is called quantum number, and it's an only integer, right? And these ENs are called discrete energy values or energy eigen values. Okay, so everything is discrete. It's not continuous anymore. Now, this wave function gives us the probability. How does it give us the probability? If I multiply it by its complex conjugate. So if we take it psi star, multiply it by psi, then we get a probability function. So, and the probability, since the particle is confined to 0 to L, the particle is definitely inside. The probability of finding the particle between 0 and 1 is equal to 1. 0 and L is equal to 1. So if I multiply the complex conjugate of psi, which is the same as sine n pi x over L, times the complex conjugate of a star times psi, and then if I take this integral of sine squared between the limits 0 and L, we get a star a L over 2. A star a is simply a squared. Okay, so that gives me a value for a, which is 2 over L. This integral is called normalization condition. The normalization condition is the condition that you use the particle exists within this space 0 to L, and you use it to find the constant A, which is the amplitude. So our probability function, which is psi star and psi n, is simply A star A, which is the square of this, so that gives us 2L, sine squared and pi xl. That gives us the probability of finding the particle at some given position x. Now, let's draw this function in the region inside the quantum well region, which is the region x equals 0 to x equals L. So if we draw this sine squared function, for n equals 1, this red curve shows that, yes, at x equals 0 and x equals L, 0, the particle cannot go out of this well. But look, the probability of finding the particle at the middle, this point here, is L over 2, is the highest. So most likely in the state E1, so this is the energy state E1, most likely the particle would be in the middle. The probability of finding the particle in the middle is highest. For n equals 2, we have this blue. If we plot this function for n equals 2, we find this curve here. The probability of finding the particle is highest at these 2 points. What are these 2 points? This is L over 4, and this is 3L over 4. So, and this point here is 0. So, in position, in energy state E2, most likely the particle would be at L over 4 or at 3L over 4. For n equals 3, we see 3 positions, okay, for the highest probability of finding the particle. And these 3 positions are here, right? Actually, these positions are not quarter, this third. This is L over 3. This is not right here. And this is 2L over 3. This is L over 3 and 2L over 3. Okay? So this is 2L over 3. Here we have L over a quarter, L over 2, and 3L over a quarter for E3, and so on. So even where the particle is not anywhere. If the particle has the energy E1, then it has to be most of the time in the middle. If it had the energy E2, it always has to be in the first 1/3 or in the second 1/3. These are the highest probabilities. If it's in the E3 state, it has to be in the first quarter or the half of the width of the quantum well, or in the third quarter point of the quantum well. Okay? Now, this state here, which is the lowest energy state, E1, is the state with the lowest energy, is called the ground state. That's a state of the lowest energy, which is most likely the energy that the state will be, the energy that the particle will be in. The second state, E2, is the first excited state. So you have to give the particle energy to go to this higher energy state. So you have to excite it. Okay? Similarly, E3 is second excited state, and so on. So most likely the particle will be in the ground state if it's not excited, if it's not given any energy. And if you give it energy, it will go to a higher state. So this problem is a very famous problem. It's electron in a well. And it seems to be very abstract, the way I'm describing it here. But it has a lot of meaning. And it's actually used in nanoelectronic technology. And it's the technology that is based on the quantum well problem. So nanoelectronic materials can be deposited layer by layer in such a way as to produce a layer in which electrons are confined and have somewhere lower energies. That would what is needed to escape these layers. Now, let's assume that you have insulator here. So if this is an insulator, and then let's assume that we have a conductor, metal here. So what we have here is metal. So metal has so many electrons. Let's assume that it has only one electron here. And then on top we have, on top here, we have insulator. Again, so we have an insulator, another insulator, okay, and we have a metal. So if we have this electron here, okay, if we have an electron here, then the electron cannot go to this insulator or this insulator. And if we have this is as our x-axis, then we can say this is our x equals 0. And we can say this is our x equals L, this point here. And this metal has a thickness equals L. So this metal is like a quantum well, because this electron cannot move outside this metal, because this is an insulator and this is an insulator. And if this is these are perfect insulators, then it's like an infinite potential or an infinite quantum well. So you can actually make this quantum well in the lab. And if it's one-dimensional, you call it quantum box. Okay? But you can make it two-dimensional. Okay? Within this quantum box, okay, you have discrete energies. But if you make it two-dimensional, then you're talking about quantum wire. And if you make it three-dimensional, then you're talking about quantum dot. Okay, so you can actually make a quantum well or a quantum box, or you can make a quantum wire, or you can make a quantum dot. If you have confinement only in one direction, confinement in two directions, or confinement in three mutually perpendicular directions. If you have if you extend the solution of the one-dimensional case to a three-dimensional quantum dot, then you have three quantum numbers, nx, ny, and nz. And your energy states are described by these three quantum numbers, which come from the confinement in the three directions. And these quantum numbers are integers, 1, 2, 3. And so you have these energies. And you also have a solution, which is in a solution in Z, in Y, and in X. And it's given in terms of the three lengths of the confinement dimensions. Okay? So the major implications of the quantum mechanics to the solution of the infinite well problem is that energies are quantized, they're not continuous. Only certain energy values that are called energy eigenvalues are possible or accessible to the particle. These energy values are separated by inaccessible or forbidden energy values, which the particle cannot assume. This picture of energy quantization is to be contrasted with classical picture where the particle energy could virtually take any value. These energies are characterized by a set of numbers, either integers, as in the example of the quantum well. They could be, as we will see later, they could be half integers, right? The probability of finding the particle anywhere in the box, 0, x, 0, less than x, less than L, depends on x. So the particle cannot be in any position. Okay, as we saw, it can be in the middle, or it can be in the first one-third or last one-third, etc. Okay, so these are very important implications of quantum mechanics. Okay, so these are the energy states, n equals 1, n equals 2, n equals 3, n equals 4, which have different energies. The ground state, the first excited state, the second excited state, the third excited state, etc. Then you have forbidden energy gaps, okay? And you have discrete energies here that the electrons can assume, okay? And this is the three-dimensional extension. Now, I told you, you could make it by simply depositing a metal on an insulator, on another insulator, and you can confine an electron. Okay, now let's look at this example which tells us how we can use this quantum box, or how we can use this quantum well. Let's look at an electron which is confined to a one-dimensional box where L is equal to 100 nanometer. Very, very thin. 1 nanometer is 10 to minus 9 of a meter width. What wavelength, right? That's a question. What wavelength of electromagnetic radiation might result from transitions between the energy levels? So, here we're implying that we could have electromagnetic radiation emission from this structure. And indeed we can. Why? Look, if we confine an electron to this quantum well, then we have different energies. N1, which is E1, N2, which is E2, and N3, which is E3. Now, if I excite an electron will be here in the ground state. If I give it some energy, some excitation, could be thermal by heat, or it can be electrical by giving it an electrical signal. Then the electron can go up here because it has more energy. Once I switch off the heat or switch off the electrical signal, then the electron drops back to the ground state. And what happens? It loses the difference in energy between E2 and E1. And therefore this energy goes out as a photon. I can excite an electron from the ground state all the way to the second excited state. And if I switch off the excitation, the electron will drop from the second excited state back to the ground state. And what happens is it will lose its energy difference in the form of electromagnetic radiation, photon. Again, it can drop from the second excited to the first excited and emit electromagnetic radiation, and then from the second to the first emits radiation. Now let's calculate. The energy En of any state, n equals 1, 2, 3, etc., is this here. So E1, the energy of the first ground state, is n equals 1. This is n. This is pi, 3.142 squared. This is h bar, reduced Planck constant squared. This is m, 2 times m in kilograms for the electron. This is L in meters. This is the energy in joules. For E2, we have n equals 2, so we get 4 times E1, which is this in joules. For E3, we have n equals 3, so we have 9E1, which is this one in joules. So now, if the electron drops from E3, the second excited state, to E1, the ground state, the energy difference will become a photon. The energy of the photon, this is here, lambda. The energy of the photon, E, is equal to hc over lambda, where lambda is the wavelength. That's one way to write the energy of the photon, or we can write it as h nu. We already, but nu is c over lambda because c is equal to lambda nu. C is the speed of light. So if we take this difference, E3 minus E1, and make it equal to hc over lambda, then lambda 3,1, that is the transition from the second, or the is state 3, to the ground, which is state 1, is equal to hc over E3 minus E1, and we get 4159 angstrom. Remember, 1 angstrom is 1 angstrom. 1 angstrom is equal to 1 times e to minus 10 meter. So that's the wavelength of the emitted photon. Apparently, this is in the red light, right? Somewhere, or maybe orange. And then for emission from E2, first excited state, to the ground state, then again, lambda is hc over the difference in energy, and that gives us 11,093 angstroms. And if we get E3 to E2, again, if we substitute, then we get 6,655. These are 3 different photons for 3 different wavelengths, so they're of different colors. So we have light emission, light of different color emission. So this quantum well concept, or quantum box concept, can be used to emit light. And this is how we do light emission from semiconductor materials. So it is meaningful. Okay, so today I will stop here, and then in the next class we will look at 2 more examples of applying Schrödinger equations to some known problems. So we stop here today. Thank you.